Right, well, thank you all very, very much for coming. I thought I'd start with just an overview of what we'll cover over the next 45 minutes or so. So we'll start with measurement and why I think it might be quite important. We'll move on to how to weigh really small things. We'll talk a little bit about light scattering, and then finally why this might be useful more generally. So measurement, right, may be important to you. You may think today I didn't do a lot of measuring, unless you were maybe hanging up some pictures. But I would argue that actually you spend most of your day in one way or another measuring. In fact, without measuring, probably wouldn't be here, right? Because this tells you the time. And it's a very useful thing that you carry with yourselves or you look at every once in a while that organizes your day, right? It's a device that tells you and tells everyone around you what time it is. So we're all synchronized and we can all be here together at the same time. So you have time, right? What other measurement do you have? Distance, right? You think, well, didn't do much distance measurement today, didn't bring my tape measure. Again, without any distance measurement, you probably have a hard time navigating the tube or the sidewalk or driving, right? What you spend most of your day is judging, maybe not measuring accurately, but certainly at least estimating distances. And the final one, which you probably didn't do any of, unlikely, unless maybe in the morning or you went shopping, is to measure mass. You didn't weigh anything, right? And you'd probably think, and I agree with you, this one really quite important, like really important. This one also pretty important. That one, don't really do much of that, right? So mass measurement, certainly the least exciting of the three. Well, I would argue that maybe, actually, this one is the most important in ways that you maybe haven't thought about, right? So let's go back 5,000 years, all right? So 5,000 years ago, most of us had one job. Don't starve to death, right? That's really all we worried about. We were living in some villages, and we had one job, which was to get enough food so that we wouldn't starve to death. And then maybe, depending on where you lived, your second biggest problem was not to freeze to death, right? But life was really quite simple. But somewhere around here, which is today's Iraq, at Mesopotamia, and that's where the first concepts or the first kind of incarnations of cities appeared, right? So here's a probably somewhat optimistic sketch of what this looked like 5,000 years ago. But what's the idea? Well, the idea is, if I'm self-sufficient, I just produce enough food or I catch enough mammoths or animals to feed myself and my family. But here, really fertile land, so you ended up producing too many apples, right? So what do you do with these apples? Maybe you trade them, right? So I give you my apples, you give me your pears. Here's 100 apples for your goat, right? So the concept of trade, and that's because you had people who were generating a surplus. And then people started specializing. So somebody would make food, somebody else would make clothes. At which point you enter the situation where you have to create some kind of concept of trade, right? So you could decide that it would always be 100 apples for a goat, but what if the apples were tiny and the goat was gigantic, or the goat was tiny and the apple was massive? You needed some kind of standard, right? And that's where you get something like the pound from, right? And the definition of the pound was that the pound is the equivalent of 7,000 grains of barley. I'm sure you're all delighted that when you go to the shops today, you don't have to count out 353 pieces of barley in order to buy your avocado. But that's been around for a long time, and in the US, in fact, that's still the standard measure of weight. You'd ask yourself the question, okay, is there a better way? Can we do better than barley, right? Essentially, what you've done is you have matter, and you've divided matter up into barley and you're comparing, matter A with matter B, just on the principle of how many pieces of barley you have. Well, it brings you to the Royal Society, right? So here is John Dalton, and just over 200 years ago, he came up with the atomic theory. And there's lots of bits to this, but the two that we're going to worry about today is, he said, well, all matter is composed of indivisible atoms, right? And atoms combine in simple whole number ratios to form compounds. And this, to some degree, formed the basis of the periodic table, right? This is what the universe is made of. So you have hydrogen here, and in fact, what you see, it's all ordered in terms of mass, okay? And you'll see that, one hydrogen atom, you need 200 hydrogen atoms, and they'll have the same mass as one mercury atom. Right? So you have a natural connection between the elements of matter and mass. Why might this be useful? Okay, so here's two compounds. And now if you're worried that you're going to have another 40 minutes of this, I promise you're going to be okay. You're going to be okay. Very little of this, right? So here is world famous RDX. And RDX, because of the atoms that are in this compound, weighs 212 grams per mole, right? And then you have 3-hydroxystanozole, and 3-hydroxystanozole is 344.49. So why is this interesting? The reason why it's interesting is that when you're on the atomic scale, mass becomes more useful, right? If I have just 100 gram of macroscopic stuff, it could be 100 gram of flour, it could be 100 gram of butter, it could be 100 grams of cheese, right? It's still 100 grams. But here, if I measure this mass, I know that I have RDX. And if I measure this mass, I know that I have hydroxystanozole, because those are the only combinations. It's only one combination of these atoms that gives me exactly this kind of mass. So what does that mean? It's basically a QR code or a barcode in your supermarket. It doesn't matter, right? It's a very unique identifier. If you measure the mass, you know exactly what you have. All right, so why did I pick RDX and 3-hydroxystanozole? Well, there you go. So RDX is an explosive, and it's one of the compounds that we're looking for when you go to the airport and they wipe your hands and they stick it in a machine. They're looking for a compound that has exactly this mass. All right, and if anything comes up that has exactly this mass, you've been a bad boy. All right? You're in trouble. And 3-hydroxystanozole happens to be what your body turns anabolic steroids into as it metabolizes it. So you take it, and no matter what you do, your body will process it, and as a consequence of processing it, it will produce this material. And there is no other natural source of it. Therefore, if they find it, it means you've, again, been a bad boy, and you've taken some anabolic steroids. So this is wonderful, right? All we have to do is we have to weigh or measure the mass of individual molecules, and we can do all of these amazing things. Where's the challenge? Okay, so here are we. Okay, 100 kilos. We're not all 100 kilos, but we're working in orders of magnitude here. Okay, so 100 kilos, right? Here's your barley, here's a cell, here's a virus, and here's water. And here's a whole bunch of numbers that don't really make much sense, right? So 10 to the 5, all the way down to 10 to the minus 23. So to put this in relation, the kind of dimensions that we're talking about, on the left-hand side, you have the existence of the universe. So that's 14 billion years. And on the far right-hand side, you have 1/millionth of a millionth of a second. All right? So the mass of one molecule of water compares to the mass of a human being as 1/millionth of a millionth of a second compares to the existence of the universe. It's a very, 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 very small number. And yet, what you want to do is you want to measure it. You want to measure it accurately. You want to measure it precisely, because that's what enables you to tell the difference between 3-hydroxystanozol and RDX. How do you do that? It's the Winter Olympics. So it's a Winter Olympics-inspired measurement, right? So if you're skiing, for a given speed and edge angle, your turn radius depends on mass, all right? The heavier you are, the less you're going to turn. The lighter you are, the better you're going to turn, right? So you see small kids on the ski slope and adults, they behave very, very differently. And it's the same concept that allows you to measure the mass of molecules. So you've got two more fellows of the Royal Society here, J.J. Thompson and Francis Aston, and they developed what's called a mass spectrometer. So what's a mass spectrometer? You take your sample, whatever it is, and you do something to it so it turns into a vapor. And once it turns into a vapor, you can zap it, and when you zap it, it ionizes, so it becomes charged. Right? So now you have charged molecules in the gas phase, and you apply an electric field, and the electric field will attract these charges. So what do the molecules start doing? They start flying down your tube. All right? So here they come out of here, vaporized, zapped, they start flying this way. The ones that make it through these two holes, they're all flying in a straight line, and now they have to go around the corner. So this is your skiing turn. All right? And if they have the same charge, but different mass, what will happen is they will turn more or less, which means the heavy ones will hit your detector over here, and the light ones will hit your detector over there. So depending on where your molecule hits your detector, you can measure the mass. Strictly speaking, what you're measuring is the ratio between mass and charge, but effectively what it allows you to do is it allows you to measure the mass of individual molecules. And this is called, here's an example of a modern version of a mass spectrometer, and it's one of the biggest workhorses of molecular analysis. So we've talked about drug testing, we talked about airport security, environmental testing, food testing. Whenever you're looking for traces, parts per million, parts per billion contaminants, mass spectrometry is your friend. Why? Because it's capable of detecting individual molecules, and it can identify them because it measures their mass very, very, very accurately. It's also used in cancer screening, proteomics, metabolomics. A lot of life science research uses mass spectrometry. And the final one, drug development. All right, so why do you need this in drug development? Well, so this is what one could call the first generation of drugs, right? Small molecules. Here's aspirin, 21 atoms, has a very precise mass. So if you're producing this drug, you want to make sure that it's pure. It's A, you made the stuff you think you made, and B, there's nothing else in there, right? So how do you do that? Well, you take your sample, you stick it in a mass spectrometer, and if you get only one peak at 180.16, then you know you have made aspirin and aspirin only, and it's pure. All right? So let's go to the second generation of drugs. So this is Keytruda. So Keytruda is an antibody-based drug. So this gross revenue in 2025 was $30 billion, one drug. Right? It's used as kind of a general anti-cancer drug, in particular melanoma and lung cancer. So this thing now has 25,000 atoms. It's a lot bigger. Right? Antibodies is what your body produces, when you get sick. Your immune system starts generating antibodies, and the antibodies start to attack specific molecules in your body. This is essentially the same thing that the drug companies do, except they don't use you as a human to generate the antibodies. They generate them somewhere else. And as you can imagine, now I no longer have 180.16. I now have a bunch of atoms and some kind of mass. Things get blurry, things get messy. The bigger they are, the more difficult it is to really just get one species. So it becomes more challenging to use mass spectrometry. The other reason why it becomes more challenging to use mass spectrometry is because these kind of molecules, they like to be in water, right? We're mostly made out of water. They're happy in water. They're not very happy in the gas phase. They don't like being turned into a vapor and sent down a tube. And this is where Carol Robinson comes in, who is one of the pioneers of what's called native mass spectrometry. So today, with advanced instrumentation and a lot of skill, you can put these kind of molecules into the gas phase and analyze them with a mass spectrometer. So the third generation, so here's an example which I find quite fascinating. So this is called Zolgensma. I don't know whether I'm pronouncing this correctly. It's quite a remarkable thing. So this is a virus, right? It's an artificial virus. And inside that artificial virus, you have some genetic material. And what this does is you get one injection for children under the age of 2 who have a faulty gene that results in spinal muscular atrophy. You get one shot, it replaces the faulty gene with a healthy one, all's good. That one shot costs $2.3 million, right? But it does take care of an extremely, extremely serious disease. Now, here, I haven't even bothered to write down how many atoms there are, because frankly, I don't really know. It's a big, big number. In other words, as we're moving on in terms of generation of drugs, they are becoming more and more and more and more complex, bigger. Why are we doing this? It's because it allows us to do things that we couldn't do with the previous generation. Right? So the antibody can target a particular protein, but it cannot replace a faulty gene. This artificial virus, which carries a gene, can do exactly that. And because of this complexity, and because of the complexity of mass spectrometry as molecules get bigger, ideally, maybe you could think of a different way of measuring mass. So let's go back to the periodic table, right? So we saw here, we have all our atoms, and they have different masses. So maybe a different way to measure mass would be if we could just count atoms, right? That would be a pretty straightforward thing to do. The problem, of course, atoms are really small, annoyingly so, right? So I can't count atoms the way I can count you sitting here in the audience. I have to use some kind of other tricks. Here's a picture from University of Oxford, I think it was taken 5 or 6 years ago, from the physics department, won the Science Photo of the Year award, I think. And what you see here is a picture taken with a standard camera like that one. This is not standard, this is much better than standard, but you get my point. And you see this tiny little dot in the middle? That's one atom. Okay, so what they've done here is they've built an experimental device that allows you to trap individual atoms, and here it is. Okay? So how is it that you see a single atom? Right? So that takes you back to why can you even see me? The reason why you see me is because there's a light source over there, and light comes out of those bulbs, and it hits my forehead, and some of that light that hit my forehead bounces off and makes it to your eye, right? Which is light scattering. And if I was made out of metal, then you would see me a lot better because that bouncing off of light would be a lot more efficient than it is with my skin. And that's exactly what's happening here. The reason why you can see this atom here is because somewhere there's a laser that you can't see, there's light that you cannot see, and the atom bounces that light towards your eye, and therefore you can see an individual atom. In other words, problem solved, right? All we need is we need a light source, and if we put that antibody somewhere into this beam of light, some of that light will bounce off, and maybe it will make some kind of shadow. Okay, good. 2 antibodies, twice as much light bouncing off, twice as strong a shadow. In other words, if we can detect and quantify the interaction of light, then we can measure mass, right? Because I have this much light for one antibody, and I have this much light for 2 antibodies, and 2 antibodies weigh twice as much as 1 antibody. Therefore, by quantifying the interaction with light, I can measure the mass. What's the problem? So here's a picture of how you might imagine visible light. So visible light is the peak of the solar spectrum, and it's a wave, right? So here's your wave. That's the size of the wave, and that's the size of your antibody. That's kind of infuriating, right? So it gives you an idea that the interaction between that antibody and that light wave probably not going to be the strongest, right? The light has a really, really hard time seeing that tiny, tiny, tiny antibody. And when we started working on this, 20 years ago, right, you took the most sensitive microscope you could find in the literature, and you came to the conclusion that you needed roughly a million-fold improvement on the best thing that anyone has ever built in order to see a single molecule. And the efficiency, I said it's bad. If you actually turn that into number, the efficiency is about 1 in a billion. All right, it's really not good. Really, really very bad. The good news is we never did that calculation. So we never had the faintest idea of how hopeless this was, and therefore, we just kind of kept going. All right? But you can look at this problem from a different perspective, and I'm going to argue that apart from that photo of that single atom in the trap, this is the smallest thing you've ever seen with your own eyes. All right? So what have we here? We have dirty water. We have oil. We have an oil film on top of water, right? And if you're not colorblind like me, then you see that there are different colors. So why are there different colors? Well, you have the light from the sun, which is white, right? Has all the colors in it. And it hits the surface. And then it gets reflected off of the surface, just like it gets reflected off of my glasses. And you have two reflections. You have one reflection from the interface between the air and the oil, because it's an oil film. And then you have a second reflection, which is at the interface from oil and water. All right? And it turns out that if this oil film is 100 nanometers thick, the light will look yellow. Okay? And why is that? It has to do with interference and constructed waves. But the bottom line is, it will look yellow. If the film is 95 nanometers thick, it will look green. Now, that's a win, right? Because 5 nanometers is roughly the size of a single antibody, in fact, smaller than that. And I've used the sun as a light source, and I've used my eye as a detector, and I can easily see something that is of the dimensions of a single antibody. Brilliant. Fantastic. Why is this so difficult? Well, there's a little bit of cheating here. Of course, we've integrated over a large area, right? So I've taken a large area, taken that 5 nanometer difference, but I've taken it over a large area. Okay, you say, well, that's not a big problem. I'm just going to add a lens, and if I add a really good lens, now I'm only integrating over 200 nanometers. So I'm not quite at a single protein, which would be 5 by 5 by 5. I'm at 5 by 200 by 200, but I'm pretty close, okay? You can go downstairs in this building. The Royal Society was founded in 1660. I got that right. I think I got it right. Yes. Yeah, good. 1660, and you can find a copy of Micrographia. So this is Robert Hooke's book, and it's, really mind-bending. Essentially, he built a microscope, took a microscope, and took lots of images of small things and drew them. I mean, it's absolutely remarkable. This is 4 years after the founding of the Royal Society. So what did this microscope look like? Here's a, of course it's not a photo, but you get what I mean, right? You have a light source, you have your sample, you have your lens, and this is where you put your eye, so this is your detector. Right? That's basically what a microscope is, all right? Fast forward all of 350 years of extreme research. Here's your lens. Here's your light source. Your eye has been replaced by a camera, and your sample is on a piece of glass. Kind of looks like the same thing, right? So if these two things are the same, if we've already been able to look at small things, why have we not been able to visualize individual molecules? Now, a key component here is this thing, right? You need a laser. Okay, the laser is essential. Here, many lasers, lots of colors, lots of laser colors, little tiny mirrors that send the lasers around different ways. And what the laser allows you to do, plus all of these little bits and pieces, is to build an extremely, extremely, extremely sensitive version of that microscope. Right? And Dan Cole and Gavin Young were two graduate students in my group more than 10 years ago now. And they really knew how to build these microscopes. So they spent years and years and years making this thing more and more sensitive, more and more sensitive, more and more sensitive. And when you do that, the first thing that happens is new problems, okay? So here is a simple version of, I mean, this is classic, right? This is what it looks like in a talk, and this is what it actually looks like in a lab. But you build a super sensitive microscope, and you put your, a piece of glass on where your sample rests, and you take your image with your fancy microscope, and here's your image, and it's just kind of grainy. And the signal that you get here is about 100 times larger than the signal that you would expect from one molecule. And what is this signal here? It's just because glass is not atomically flat. And it's a little bit wobbly, and because it's a little bit wobbly, it makes a little bit wobbly images, and those little bit wobbly images produce a signal that's 100 times bigger than what you're going to see from a single molecule. So in principle, you may have built a microscope that's good enough to see one molecule, but unfortunately the glass is not cooperative. The other problem is, because the signal is so big, if this glass, which is a slide maybe 5 centimeters by 3 centimeters, if that moves as much as the size of a hydrogen atom during your measurement, you're done. Because all you're going to see is the glass, you're not going to see the molecule. So not only do you need lasers and sensitive microscope, you also need really stable microscopes because your glass is not allowed to move. So here is what a stable microscope looks like, at least the first version. All right, so this is how we achieved extreme stability. Step number 1, vibration isolation, very important. If there's any vibration, right, the vibration will carry through and your piece of glass jitters around. So the way you solve vibration isolation is you go on the internet, and you purchase some inner tubes for wheelbarrows. And you partially pump up the inner tubes for wheelbarrows, and you put your microscope on these inner tubes for wheelbarrows, and fantastic, you have air suspension, right? The second problem you have is thermal drift. So if things become warmer or colder, everything changes. That's a big problem. So the way you solve that problem is you spend a lot of money on a gigantic piece of metal, because gigantic pieces of metal move in temperature very, very slowly. You put all of your little lasers and mirrors inside that piece of metal, and you put it inside this box. So this thing is really quite heavy. And then the final problem you have is sound, right? Or any kind of perturbation in the environment. And this is a very professional way of solving that. That's a styrofoam box, right? Now you're safe. And when you've done all of this, you can do the experiment. So here's what the experiment looks like, or looked like, I should say. So you switch off your laser safety. You open your box. There you see your little lens, your microscope. No laser at the moment. You take a tiny, tiny droplet of water with your protein in it. You carefully put it on top of the slide. You close your laser safety box. You turn your laser back on. Ta-da. Right? And every one of those little black dots is one molecule. Okay? One molecule binding to the surface. Now, I should tell you, you think, oh yeah, your stable microscope, your inner tubes, that's just a joke. So when we did this experiment originally, when we had this, the only way you could do the experiment was with 2 people. One person was sitting in front of the computer and holding the mouse. The other person was holding the pipette and standing next to where the sample was. The person with the pipette would put the sample on, would move the hand away, take a deep breath, not move. The other person would click, and then everybody would be stationary for 30 seconds. Which means the longest experiments we could do was as long as people could hold their breath. Because the moment they exhaled, the experiment was over because your cover slip moved by a hydrogen atom and it was all done. But with this thing, you could see actually quite happy. All right. So what do? I build microscopes, right? And we built this thing, and we just make it. How sensitive can we make it? How sensitive can we make it? More and more and more and more and more. And then we had this amazing microscope. So what are we going to do with this? In comes the all-important pub, right? And my colleague Justin Benesh, who's a does mass spectrometry for a living, and he also likes the pub, so him and me went to the pub. We had a beverage. I said, Justin, what are we going to do with this? Justin says, maybe we could measure mass. Okay. Well, here you go. Right? So how does this work? You have your piece of glass, you have your protein that's floating around in solution. Turns out biomolecules like to stick to glass. It's just what they do. And one of these molecules sticks to the glass, and you look at your camera, what you'll see a tiny change in the light intensity. Right? So you can see here, what is this? 1.2 million 2,000 and 1.2 million 10,000, right? So it's a tiny, tiny, tiny percentage. But because we worked so hard on eliminating all the noise sources, even though it's a tiny change in absolute terms, we can very clearly see it. And we can quantify it, right? We can measure exactly how big that change is. And the size of that change is proportional to mass. All right? So if you now take your sample and you put it in one of these machines, each of these black dots that you saw in the previous movie, the size of the signal is now one of these white dots in the scatter plot. And you'll probably agree with me that you have a band here, and you have a second band here, and you have a third band here, and then maybe a fourth one and a fifth one, right? And you look at the numbers that are at the center of the band, right? And you see, well, this number times 2 is kind of that number, and that number times 3 is that number, and that number times 4 is that number, and that number times 5 is that number. So what's going on? Well, the first peak is 1 protein, and the second peak is 2, and the third peak is 3, and the fourth peak is 4, and the fifth peak is 5. Okay? Which means you can now measure mass. This is the size of the signal, this is the mass, and you get a straight line, which means you can take any molecule, you can put it into this machine, and by measuring the signal, you can measure the mass. Now, what's quite remarkable, you look at the error here, and the newest versions of these instruments, we're better at measuring the mass of one molecule than your average bathroom scale is measuring your mass when you step on it. This is really quite remarkable. So we can measure one molecule with a precision of a few percent. All right, so here we were, October 27th, so this is eight and a half years ago, almost, just a bit more than 8 years ago. So here's this box, right? And it turns out that actually this could be quite useful for a lot of people, right? You have developed an antibody which is supposed to bind to a specific target. You want to know if it binds. Well, here's mass A, here's mass B. If they bind together, it's mass A plus B. I can see all of these things, right? If I want to look at my viral vectors, whether they have a gene inside or not, they have different mass. It's really quite universally useful. It's actually quite easy to use, as you saw in the video. And in fact, you could probably walk up to the machine and do an experiment yourself. It's really not that hard. The equipment is not as complex as what you need to do mass spectrometry. You get a really quick answer, right? Because you saw the little dots, you get an answer in about 30 seconds. And you need very little sample, right? Because you're measuring individual molecules. In fact, we waste, we use 10,000 times or 100,000 times more sample than we would need, just because that's the smallest amount you can actually physically move around. And then, this is brand new, and then we just started. Mass spectrometry has been around for 100 years. I mean, all the amazing things we could do in the future. The big problem you have is there's exactly 2 people in the world that can build this thing, and it only works in one basement in the University of Oxford. But the people who actually want to use the technology, they don't know anything about microscopes, they don't care about microscopes, they don't care about lasers, they don't want to put them together, not interested, right? So how do you bridge that gap? Here's a brainwave. You look on the left and you go, kind of looks like a box, right? It kind of looks like an instrument. You thought, we make it look more like an instrument. So you see between October 2017 and February 2018, we made this little prototype. I admit now, with 8 years later, I don't think it looks quite as much better than the one on the left as I thought at the time, but we were very excited. It was smaller and had round edges. It was amazing. And we thought, we're ready. This is a fantastic idea. We're ready. We're going to go to a conference. we're going to go to conference. So we went to San Francisco, and there was no company. We just had this prototype. So I had to invent a name when we registered, and this was the name which turned out to be trademarked, so we had to change the name. And this was our booth, and our booth was purchased at Target down the road, where we went and bought some lamps, a television, and some bed linens, right? Constructed this booth on a rickety table and thought, oh yeah, that's a fantastic idea. What we're going to do is we're going to do some demos. Now, just to give you an idea how this went down, Dan here built this microscope in Oxford, and 2 days before we went to San Francisco, we realized that when we took the microscope and put it into one of those cases that you see photographers fly around with, when we put the microscope in, unfortunately, it was 34 kilograms. And the heaviest thing you can put on a plane is 32. So conveniently, Dan had to take the microscope apart, ship it in 2 bits, fly it to San Francisco, and then reassemble it in his hotel room, which made him extremely nervous because he was worried about what the cleaners might think if they come in and see all of these bits lying around. So successfully, he reassembles this thing, he puts it on the table, and he does live demos. And there are your little dots. This is a Biophysical Society meeting. And no company, just this thing. We sold our first instrument. Somebody walked up to us and said, I'm going to be your first customer. I'm going to buy this thing. Right. And that kind of gave us enough to go and raise some money, right? So you go to venture capital and you raise some money. You think, oh, venture capital money, we're going to have foosball tables and slides. And so here's our foosball table slides. This is our first headquarter. So this is in George Street in Oxford. This is a burger joint, a news agent. In fact, the person who has an office here, a software company, is sitting over there, Chris. He had 2 spare rooms. Like, hey, this is perfect. This is where you build the most sensitive microscope in the world. So this was our assembly, and this was the office. And indeed, we did build it. So in October, 3 months later, here is unit number 1, very professionally packed. We then had to carry this with a lot of help from Chris's employees, carry these crates down the stairs in this 1920s Art Deco building, put it on a truck, and send it to our first customer. So here we are 7 years later, right? So we've got a new name, refined. There's, I think, almost 600 instruments sold now, more than 50% to industry, more than 10,000 users, 1,200 papers where people have used the technology. Not that somebody went, oh, this is a nice thing. They actually use the thing for what they're doing. More than $90 million investors, 160 employees, headquarters in Oxford and Boston. And we were just on the Sunday Times fastest growing tech company list. How do people use it? Well, next generation therapeutics, you guessed it, right? It's simple, it's quick, it gives you the kind of answer you need. mRNA, you'll remember mRNA from 5 years ago, 6 years ago. Well, we won't speak about it. But these are big particles. Heterogeneous is a good thing to measure. These viral vectors, and for kind of the next generation of antibodies that pharma companies are working on. Throughout drug development and control, and really across the full breadth of life science research, because it's a quick and easy tool that gives you unique information with very little sample in a very short amount of time. And in fact, there's now a second startup that uses a similar technology, but it's looking at how batteries charge. Turns out that's also something you can do. And now, there isn't just one silver box with a bunch of curves. There's, a whole lineup of different instruments and automation and all the kind of things that industry and users require. All right, so you've almost made it. Just one little kind of personal message, I think, at the end, right? This started out as really, really fundamental research, right? What's the smallest thing we can see? That's what we did, all right? And when we started, it was accepted in the scientific literature that this will never, ever work. There is no way anyone is ever going to see a single molecule with light scattering. Not going to happen. You're 6 orders of magnitude away. You need 8 or not going to happen. Okay. Even if we had dared to say to anyone back then, look, listen, if you just give us some money, we're going to build this microscope. Don't worry, in 10 years' time, we're going to be able to do this, right? That would have been the end of my scientific career. Right, that's it, I'm done, I'm finished. There's no way, no, totally, that's nuts. It's never, ever going to work. Today, more than 100x return on taxpayer investment, right? This is taxpayer-funded, curiosity-driven, fundamental research, but it's really returned, right? It has had an impact on the economy. We've employed 150 people. It's enabling new science. We don't even know where this technology is going to go, right? It's only been around for 7 years. And, it was interesting because I spent most of my life in academia, and then I got a little bit of a kind of peek into the venture capital investment world. And there you realize, completely accepted, that you take risks, and most of your bets don't work out, but a few of them make it big. And that's how, in the end, everything's okay, right? And if you really want to have a big change, a big breakthrough, really change, the way consumers interact, or, whatever it is, you're going to have to take big risks. And of course, what nobody talks about is the 740 versions of Facebook or whatever that have failed. We only see the one that has worked, right? So there's lots and lots and lots of failure. It doesn't make any sense to accept science to work in any different way, right? There's a reason while many of the breakthroughs that happen, for example, in the pharma space, don't come from pharma research. They come from pharma buying startup companies that do things that are too risky for them, right? And they skip that step and come in. If we get rid of this fundamental curiosity-driven research, what happens is you really, most of the time what you'll end up doing is incremental work. Because that's what's likely to succeed, and it's going to be a little bit better, and we can see what's going to come out on the other. Yeah, wonderful, you go and do that. But that's really not going to make transformative change. So, this is actually going on right now. And, it's understandable. This is taxpayers' money, and there isn't money for anything, so, why should we be funding stuff where we can't see today what the impact on society and the economy is going to be? And the answer is, you have to take risk, and you don't really know where this is going to take you. So let me finish by saying thank you. So I need to say thank you to Justin, who's just a massive driving force behind all of the science, and then Carol Robinson, who's been my mentor in Oxford, and really guided me throughout my career. But I want to finish with the most important people. These are the people who actually do this, right? I stand here and I tell you a story, but there's a whole bunch of them in the audience, and I encourage you to speak to them afterwards if you get the opportunity. They are the heroes. Now, why are they the heroes? Because, of course, what you see here sounds like, oh, yeah, so you had this idea, and then you tried something, and it worked, and oh, wonderful, everybody's happy. What you don't see is all the failures. And I can guarantee you, and you can speak to my students afterwards, they will confirm, most of what we do are catastrophic failures. And that's a good thing, because that's how we learn. Right? If we just did things that we think were going to work and then they worked, it would just confirm what we already know. What's the point? We haven't learned anything new. We take big risks, and many of them will spend 2-3 years just failing, and they have the perseverance to go back and make these experiments work. And they are the ones who deserve the applause at the end of this lecture. Thank you very much.
Well, first of all, thank you very much for that lecture. I think there were many good lessons in there. One of which is that we need young people in science. because they don't know how hard some problems are, so they will just keep working on them. And, you know, that's a really important thing. We really need young people in science. Well, Professor Kukura has kindly agreed to take questions. So if you would like to ask a question, can I ask you to put your hand up? We do have some people with microphones. So if you raise your hand, someone will come to you with a microphone. So we'll take, first of all, there's someone with their hand up on the left, and then just along the same row, someone else. So we'll go for you two first. Go ahead.
Yeah, I'm over here. Sorry, that was a great talk, and I'm a pretty extensive user of mass photometry on the 1MP and now 2MP. But I was wondering, where do you think the actual limit will be for the lower mass end? Because right now that's approximately 40 kilodaltons or so. Do you see the technology pushing past there at all, or is that just a hard limit?
Well, I mean, there's what's theoretically possible, and that's what we've achieved. Where's Jack? Jack, where are you? There he is. There's Jack. Jack's been working on this for the last 2.5 years. He's gotten done factor of 2 at least, right? Yeah. So theoretically, I think an order of magnitude is completely realistic. There are some sources of noise that we don't understand. We've only been trying to understand them for the last 8 years, and we've made very little progress, but we're kind of getting there. But there's no reason why we shouldn't get, I'd say, to the kind of 5 kilodalton regime.
Thank you, that's amazing.
Thank you. There's a question here.
Hi, yes, thank you for the very exciting lecture. My question was, does the shape of the molecule kind of matter? And if you have only kind of one sample, one molecule that you're measuring, what is the worst shape that is the hardest to kind of measure, if that is actually a rule?
Yeah, that's a very good question. So the big picture answer is, remember the wavelength of light and the size of the molecule. So as you can imagine, the light has a very hard time telling whether the molecule is shaped like a banana or shaped like a watermelon, right? Because it's just so small. But again, Jack has shown that if you use polarization, so you can polarize your light, and if you use certain polarizations, then you can become shape sensitive. And conversely, if you don't want to be shape sensitive, you do a different polarization, and then it doesn't really matter. But the answer is a little bit. And
I think, was there another? Yes, there's a question towards the back, near the aisle.
Hi. First of all, thank you for your talk. I really appreciate how your research break through all the impossibles. I'm a PhD student as well, so I know how painful it is to work. And so my question is, hopefully I didn't read it wrong because I'm sitting pretty far here. I think you mentioned your second startup is something about with batteries. So yeah, without disclosing too much of your business secrets, can I just get to know how actually the battery relates with your
So it's not my startup.
Right.
I'm not involved. Some of my former students have started this company. So how does it work? So light scattering, right, if we go all the way back to the beginning, is you have an electromagnetic wave, right? You have your light. And what it really the reason why it bounces off of things is because it interacts with the electrons that surround your atom, okay? Right. So there's some interaction. So in some terms, it depends on how floppy these electrons are, okay? If they're really floppy, you get lots of scattering. If they're quite rigid, you get very little scattering. So when you're charging or discharging a battery, you're changing ion densities. And when you're changing ion densities, broadly speaking, you're changing the floppiness of electrons. So you can see when a battery is charging and when a battery is discharging by looking at the amount of light that is being scattered. Now, why is it here? Because a lot of batteries now use nanoparticles in the charging process, and it's very difficult to figure out how this discharging cycles affect these particles. And with this technology, you can actually visualize it. So you can see a charge, and you can see discharge, and you can see how it changes as a function of charge-discharge cycles.
Got it. Thank you very much.
And so we have a couple of questions down the aisle here, gentlemen, and then another question there.
is there scope to one day produce a sort of MEMS miniaturized version, a low-cost miniaturized version of this sort of tech?
Yes. I mean, in principle, right? So it turns out that a lot of the individual components in this machine are actually not that expensive. And a big problem is just unit numbers, right? Your iPhone has one of the best cameras anyone has ever seen. Why? Well, because they sell 1 billion of them. So if you make a lot, then the price comes down. We've sold 600, right? So there will have to be some kind of synergy between adoption and unit numbers, and then there is a lot of scope for the price to come down. I mean, is it going to be a handheld thing? I think that's going to probably take a little bit of time. But certainly the price will come down, I think, by an order of magnitude within 5 years and make it much, much more widely available.
I think we had another question close by.
Hi, I'm sorry, I have two. My first one is kind of, how much did you face any problems kind of with the kind of quantum aspect of it? So kind of the wave-particle duality of light, was that a factor when you were thinking about kind of mass photometry? I don't know if I said that right. But also I was wondering how it was going from a very kind of theoretical background in kind of theoretical and physical chemistry and taking that into a very kind of practical industry-based kind of profession.
Yeah. So this is not a quantum technology. I mean, I wish I could have said that. I think that would have made my life easier fundraising at some point. But quantum doesn't really play into it. You can describe all of this with classical models. The transition was a learning experience, mostly because on the academic side, you spend a lot of time making particular steps, and then maybe you make a breakthrough. And you're like, oh my God, people have been trying to do this for 30 years. This is super exciting. I'm sure this will be a successful startup. And then you realize very, very quickly that nobody cares about your scientific breakthroughs. At the end of the day, people have to part with their money, and they have to decide between your product and another product. And either you provide answers that the competition doesn't, or you do it quicker, or you do it cheaper. You have to have something. It's just cold, hard facts. And at that point in time, everybody says, oh, that's really cute, well done. But I'm still going to buy the other thing. So the toughest lesson was to accept that what you've been working towards your whole life, yes, matters to you and matters to the scientific community, but commercially is not that relevant. You then have to create I wouldn't say you have to create the market or you have to create the narrative, but you have to make sure that the product you have created, you have made, actually has a market.
Thanks, and I think one right at the back there with the question, and then a couple further forward.
Thank you for your talk. So in terms of microscopy, so we use SEM microscopes for checking the surface smoothness, and we use vacuum for it. In your case, does it make a difference if you use a vacuum or not, especially because I noticed you mentioned there's a bit of noise on the background?
Well, I mean, we can't use vacuum because we do everything in liquid, right? We do everything in water. So, as far as you're concerned, that's the filthiest place you could possibly be compared to ultra-high vacuum in SEM. We now believe, we always blamed the water. The water, it's your fault, you're the problem. We actually got some results relatively recently, which turns out we blamed the wrong one. It's not the water, surprisingly enough. It doesn't seem to be the liquid. The liquid behaves very well. I still can't tell you what it is. It's only 8 years in the running, but Jack will get there, I'm sure.
And I think we had some questions right in the middle here.
Thank you very much for a spectacular lecture. My question is about relation between academia and business. So you mentioned that you got to 100x return for taxpayer. What exactly do you mean here? And when exactly did intellectual property appear here, and who does own the intellectual property?
Yeah, so certainly at the time when we started the company, we would not have been able to start the company without background IP. Nobody would have given us any money without IP protecting the core technology. So it was extremely important. The IP is owned by the university, and it's licensed to the company. And as far as I can tell, it's a very efficient process, and much more generous than it would be if you're working for a company, right? If you're employed by a company, then the company owns all the IP, and you get a sandwich and a pat on the back, and off you go. So I think that process works very well. Remind me, the second question was?
Intellectual property is still owned by the university,
It's still
and
owned,
it was licensed to the company. Okay, thank you.
So a question here, and then perhaps one last question at the front. Oh, no, there was a chat, and then a question at the front.
Yes, so you mentioned, or I think you kind of referred to it maybe 2 questions ago, about how the liquid is well behaved. But when measuring at the atomic level, do you have to contend with like Brownian motion, especially considering the sensitivity, for example, with the glass, if it moves one diameter of 1 hydrogen, is that a problem? Yeah. Maybe it helps to maybe freeze the sample or something before.
Yeah, I mean, so the good news is that the resolution of the microscope is so bad, it doesn't know that there are water molecules. It has no idea. Like, as far as the microscope is concerned, that doesn't exist. And in fact, the only reason why this works is because, you saw the little dots, okay? You never saw a protein go, ooh, right? It just appeared. And the reason is it moves way too fast. And while it's in solution, it's, going so quickly, we'd never be able to see it. The only reason why we do see it is because when it sticks to the glass, it doesn't move, right? So it's not there, and then it's there, and it doesn't move. And that allows us, gives us enough time to average the signals so that we can actually see the protein.
Thank you. And question at the front? We mentioned we'll get you a microphone just so people online can also talk. There we go.
The importance of getting young people into science. I wondered how you felt the state system in this country is stimulating and nurturing interest in science. Are ever more young people taking GCSEs in science subjects? Are ever more young people taking A-levels in these subjects? Where are we?
Do you know better than me?
So, I think
this is the Royal Society.
So the Royal Society does have an education committee, and I don't have the statistics off the top of my head, but there has been a lot of work done looking at, I think, most recently, at the curriculum, because I think making sure that when we teach young people, we're teaching them modern subjects, that they're really getting the most exciting, up-to-date things in the curriculum. Everyone talks about AI, about data literacy, helping people understand the most sort of relevant things. I think it is a constant challenge in terms of numbers. They do fluctuate actually. At university, I think we still see a good sort of a number of people choosing the hard sciences, physics, chemistry, and so on. But it's not easy. You do see fluctuations, at the school level, and I think that's something we're very keen to make sure that we address.
I mean, I can give you maybe an international perspective. One of the things that I think this country does exceptionally well is you go to university, and it doesn't really matter what you read, right? You can go read physics, or you can go read classics. And, if you still want to become a lawyer or a medic or, whatever it is, you can do that. In other countries like Germany, where I came from, right, if you want to go into business, you have to do economic, and it's very, it's much, much more difficult to move sideways. And of course, that's a real problem, because a lot of people will not choose subjects that they consider difficult from an employment perspective. So they really thin out. Whereas here, well, I want to do chemistry, I'll probably still get a job, right? I got lots of friends who did chemistry and they got a job, and it's going to be fine, I'm going to do some chemistry, right? So in my mind, at least at the university level, if society is able to maintain that open-mindedness and accept the fact that what you're hiring is somebody who learned how to think, rather than somebody who learned how to design a particular part of a bridge. That is a huge thing you can do to promote heterogeneity at university level.
And I think also at younger levels, making sure that we can have in schools breadth of subjects, that we don't force young people to choose too early. Again, I think that's another thing that we would like to see, that breadth of opportunity.